rational root theorem. Suppose you want to solve this cubic polynomial. First we have to get a factor. Then by trial and error you have to get to one root. You substitute different numbers, 2 or 1, 3. Guessing a number, you have to check whether you are getting 0. For example, suppose x is equal to 2, you are getting 0. Then x minus 2 is a factor. Then once you get to one factor, you divide this by that factor and then you will get a quadratic polynomial. But guessing a number as a root and solving is not easy. Then this rational root theorem helps us to come to a conclusion. What are the possible roots? Let us see rational root theorem. This is a polynomial equation with integer coefficients. That means an, a1, all are integers. Coefficients are integers with an not equal to 0. a0 also not equal to 0. Then if p by q is a root such that pq is equal to 1, that means here greatest common divisor of p and q is 1. Then p should be a factor of a0. Q should be a factor of an. Now let us see what will happen if it's a monic polynomial. Monic polynomial means an should be 1. Then if an is 1, compulsorily q should be plus 1 or minus 1, but because it should be a factor of an is 1. Monic polynomial an is 1, that means for q there are two possibilities, either it should be plus 1 or minus 1. Then q is plus 1 or minus 1, that means root should be an integer. That means for a monic polynomial with the integer coefficients, root should be an integer. A monic polynomial with the integer coefficients cannot have a non-integral rational root. If there is a rational root, it should be an integer. Let us see this example. It's a monic polynomial because coefficient of the leading term is 1. That means an is 1. An is 1, then q should be plus or minus 1. So then p should be a factor of a0. In this example, a0 is 20. Then 20, these are the factors, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 10. So these are the possible roots. P should be a factor of a0. So a0 is 20. So these are the possible roots. Then we have to check. Then when we substitute 2 in this expression, you will get 0. So 2 is a root for this polynomial equation. Then x minus 2 is a factor. Then you divide this by x minus 2. You will get this quadratic polynomial. Equating it to 0 and solving, you will get 2 minus 2, 5. So the rational root theorem will help us to guess the numbers as a root. Now let us apply rational root theorem for this monic polynomial equation. Monic polynomial, so an is 1. When an is 1, q should be plus or minus 1. In the p by q is a root for this, then q should be plus or minus 1 because q is a factor of an. Here an is 1. Then p is a factor of a0. this p should be a factor of a0. But in a given example, a0 is minus 6. So the 6 factors are plus or minus 1, plus or minus 2, plus or minus 3 and plus or minus 6. So these are the possible roots. That does not mean that all of them are the roots. When you solve this quadratic equation using the formula minus b, now here b is minus 5 plus or minus root of b square minus 4ac by 2. So here minus into minus plus, so 5 plus or minus, then square root of this is 7. So 5 plus 7, 12 by 2, 6, 5 minus 7, minus 2 by 2, minus 1. You can see 6 and minus 1 are the roots. So it is integer. The roots are integers. Now you see this example. It's also a monic polynomial. Then factors of 4, plus or minus 1, plus or minus 2, plus or minus 4. But when you solve this equation, you are getting plus or minus 2i. Take this plus for the other side, so minus 4. Then x square is minus 4, so x is equal to plus or minus square root of minus 4. So plus or minus square root of 4 is 2. Then square root of minus 1 is I. So its solution is plus or minus 2i. None of this numbers are the roots. So from this is clear, rational root theorem helps us to guess the root, but it does not give us the roots. Now let us use rational root theorem for solving this polynomial equation. In this problem, an is 2, a0 is 3. Then as per rational root theorem, if p by q is a root and greatest common divisor of p and q is 1, then p should be a factor of a0. That means p should be a factor of 3. Q should be a factor of an. That means 2. That means the possible values for p is 1, minus 1, 3, minus 3, because these are the factors of a0. 3. And possible values for q, factor of an, that is 1, minus 1, 2, minus 2. Using this p and q, the fractions possible is plus or minus 1 by 1, plus or minus 1 by 1, next plus or minus 1 by 2, plus or minus 1 by 2, then plus or minus 3 by 2, plus or minus 3 by 2, then plus or minus 3 by 1. So these are the possible fractions which we can form using this p and q. There are 8 possibilities: plus 1 by 1, minus 1 by 1, plus 1 by 2, minus 1 by 2, plus 3 by 2, minus 3 by 2, plus 3 and minus 3. Then substitute these values in this equation. You can see when you put x is equal to minus 3 by 2 in this equation, you will get to 0. So minus 3 by 2 is the root, is a root. Then all the other values are not the roots. Minus 3 by 2. Minus 3 by 2 is a root, because when you put x minus 3 by 2, you will get to 0. Then as per remainder theorem, if minus 3 by 2 is a root, x minus 3 by 2 should be a factor. Minus into minus plus, so x plus 3 by 2. If x plus 3 by 2 is a factor, its multiple, integer multiple also will be a factor. So this you multiply by 2. So it will become 2x plus 3, because this 2 will get cancelled. So 2x plus 3 is a factor for this. When you divide this by 2x plus 3, you will get x square plus 1 as another factor. Equate it to 0. X square plus 1 is equal to 0. That means x square is equal to minus 1. X is equal to plus or minus square root of minus 1. Square root of minus 1 is I. So its solution is plus or minus I. So the roots are minus 3 by 2, then plus I and minus I. So this is a cubic equation, a polynomial equation of degree 3. So number of roots also is 3. Minus 3 by 2 I minus I. Thank you for watching.